Hello, my name is Jeremy, and I worked with Comfort and Udbhav under the mentorship of Dr. Seshaiyer to address problem number 3 of SCUDEM 5. The problem we chose to address was the preferential evolution of resolution methods in refugee settlements in Uganda. Our models operated on the premise of 3 distinct methods of resolution: arbitration, resolution through courts; mediation, resolution through third party; and negotiation, internal resolution. Before creating our fundamental model, we laid down foundational assumptions that regulated the interactions of our populations. They are as follows. The population stays constant over the interval. The total crime frequency is kept constant. Crimes are generalized into three types: minor, medium, and major. Each resolution strategy works best for a different type of crime. The population is rational and willing to change methods. And lastly, people only change their views after interacting with someone who has an opposing viewpoint. We chose to use a compartmental SIS-based model. This is our model diagram, which shows the basic movement of the populations. Individuals can favor a resolution method and be in that compartment, or be undecided, which puts them in the susceptible category. By interacting with other bias members, biased individuals can become more open-minded and move back into the susceptible compartment.
These are our model's parameters. Note that X, Y, and Z are the proportion of minor, medium, and major crimes, respectively. The alphas correspond to the rate at which an individual adopts a resolution strategy method, and the betas correspond to the rate at which interacting with someone with a certain resolution method makes you more open-minded. You may have noticed that the alphas are functions of X, Y, and Z. We split our total time interval into 5 subintervals and assign proportions of minor, medium, and major crimes that occur in each subinterval. Thus, from t equals 0 to 10, resolution methods that are better at dealing with medium and major crimes will have a higher infection rate, alpha, and thus be adopted by more people. Here are the equations that define our model, 4 equations for our 4 compartments. On the bottom, we express the alphas as linear equations in terms of the proportion of minor, medium, and major crimes. You can see that alpha sub A, arbitration, is best at dealing with major crimes, Z, while alpha sub N, negotiation, is best at dealing with minor crimes, X, and mediation is almost a middle ground.
This is a graph of our simulated model for 50 weeks. Notice how the strategies are relatively even until t equals 20, when we start having lots of major crimes. And by the end of the simulation, the majority of the population supports one strategy, arbitration. This is because our model ensures that once a strategy reaches a slight majority, the infection term quickly overwhelms the other infection terms, and that strategy quickly ascends to dominance. In this graph, we show the influence of a higher birth and death rate, mu, with everything else the same. Here, more individuals are born and thus enter the susceptible compartment, and more individuals die or leave the other 3 compartments. The final outcome after 50 weeks is that mediation wins out, as arbitration was unable to reach a majority between t equals 20 to 30 when there were lots of major crimes. In this graph, we see the effect of introducing new populations into the model. We ran our model in 10-week intervals and added incoming populations with pre-existing beliefs between each run. At t equals 10, we added 50 new susceptible people, which had no effect on the overall proportions of each strategy. At t equals 20, we added 20 new negotiators who kept the strategy alive until t equals 30, and in this time, arbitration died out. At t equals 30, we added 20 new negotiators and 20 susceptibles, which were insufficient to keep mediation from becoming the dominant strategy. Finally, at t equals 40, 50 new negotiators were added, but were absorbed into what most of the population preferred, which is mediation.
Our first extension introduces the concept of economic injections into mediation efforts. We implement this by using the concept of optimal control to minimize monetary injections while maximizing both negotiation and mediation populations. With optimal control, we have an objective function, j of I, that denotes the variables that we are maximizing and minimizing. The primary goal of the model is to maximize mediation populations while minimizing both the amount of economic injections and arbitration populations due to the high costs and resources needed to fund that resolution method. Shown below is how the monetary injections will affect the previous equations, allowing for us to control the speed at which susceptible individuals are influenced by mediation favoring individuals. To determine our optimal control, we use Pontryagin's maximum principle to derive conditions for our optimal control and corresponding states. Shown are lambda functions that are adjoint functions corresponding to S, A, N, and M respectively. Using these functions, we're able to solve backwards in time to find our control variable I. Here's a brief overview of the process. First, we solve the model in a forward fashion. Then we solve backwards in time using our lambda functions. Once solving backwards, we check the resultant value using our switching function, which, depending on if it's positive or negative, denotes whether the control should be at its upper or lower bound. Then we stored the adjusted control values and redid the forward sweep. We continued this process until all populations and the control converge within 1/1000th of its previous iteration. Shown in these graphs are the result of implementing an optimal control. This first graph shows a simple model of no monetary injection. In the middle graph, an optimal control is introduced with an ability to increase affinity by 2. In this one, we see very quickly that instead of arbitration becoming the most favored, mediation eventually becomes the strongest resolution strategy. In the last graph, a lower bound of 1.05 is set, essentially showing the effect if small economic injections were consistently given, even after the switching function was satisfied, which obviously shows a very quick domination by mediation.
Our next extension was parameter estimation. Specifically, we use a novel technique in the literature called physics-informed neural networks, or PINs, which enable us to learn the solutions and parameters of ODEs and PDEs. The fundamental idea is to leverage the power of neural networks as universal function approximators and apply them to our model. Specifically, we use a simple feed-forward deep neural net with 1 input, time, and 4 outputs for our 4 compartments. We train on data from the forward solution of our model, and then in TensorFlow, we can optimize for whatever parameter we're estimating. The novel idea with PINs is to use not 1, but 2 types of loss. First, we have our SSE sub u, which is the sum of squared error between what the neural net predicts for a given t and our real data, which we're training on. The second part is SSE sub f, which is a symbolic loss, calculated on all t values across the interval. So here's an example of part of our symbolic loss. This is the dAdt equation in our base model, but the derivative has been moved to one side, so we're left with an expression that we know should equal 0. We can use this expression as part of our loss, and it massively speeds up the neural net's convergence because it is now incentivized to maintain this relation and make the expression equal 0. We do this with all 4 of the equations in our base model, and we add one more equation, which is that the total population is constant, which just helps it converge faster. We decided to estimate the infection rates, so the alphas. Since crime rate varies and parameter estimation only makes sense with a single parameter, we only ran the PIN on data from a single interval, so the parameters were constant during that interval. After training with the Atom optimizer, we achieve an average error of around 5% for the alphas. This is pretty good, but future work could involve normalizing our equations and using recent neural net techniques like dropout and L1, L2 penalties to improve accuracy.
Our final extension is a new approach that incorporates mixing patterns between individuals of different viewpoints. We expand on our model and treat individuals who favor each resolution as 3 different groups. These individuals can either be biased, indicating they are capable of becoming open-minded by interacting with other groups, or extreme, meaning they have settled on a view and are unable to be convinced otherwise. Thus, we redefine beta to be the product of the fraction of contacts made by group I with group J, F sub ij, and a total number of contacts made by a group, C sub I. In addition, we introduce pi, which is the proportion of individuals in a group that mixes exclusively with other group members. Therefore, we display the updated equations for this model on this slide. Now we can control pi to explore different mixing patterns. In the top set of subplots, pi is the same across all the groups. The leftmost subplot corresponds to proportionate mixing, where group members mix at rates relative to their activity levels. The middle plot shows preferred mixing, where only a fraction of the group mixes proportionally, while the rest mixes exclusively within the group. Lastly, the rightmost plot corresponds to like mixing, where all group members mix exclusively with each other. Notice how with like mixing, individuals become extreme sooner than in other types of mixing. In the bottom plot, we vary pi across the groups. Here, notice how a higher pi value corresponds to a larger group size. Therefore, from this model, we can conclude that more intergroup mixing makes it harder for individuals to become more open-minded, thus promoting extreme views towards the strategy. Some avenues for future exploration include turning our piecewise crime rates into a smooth function and making our ODE equations into PDEs that depend on crime as well as time. Next, we can generalize our model to any population with differing belief systems that compete. Lastly, we could add complexity to our model by introducing new compartments, like an outside world compartment that would obviate the need to add incoming population manually. We use MATLAB, Python, and libraries like TensorFlow, LaTeX, and Google Cloud in our analysis. Here are references, and thank you for listening.